So we have an induction proof on our napkin for the statement that the sum of the reciprocals of consecutive pairs of natural numbers, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 all the way up to 1 over n times n plus 1 is n over n plus 1. So we have all of the work on our napkin, and our napkin includes a place where we did some work manipulation to both sides of an equation. And my claim from last week is that from a stylistic perspective, we often like to present proofs of equations or proofs of inequalities by working from one side to the other, rather than trying to operate on both sides. So let's just see what that looks like in this case. So let's quickly dispense with the base case for this proof. When n equals 1, we had 1 over 1 times 2, so just a single term on the left-hand side. On the right-hand side, 1 over 1 plus 1. And since both of those are equal to 1/2, we have proven the base case. All right, so I just want to dispense with that one quickly so that we can move forward to the inductive case. So the inductive case begins with the inductive hypothesis. So in the inductive hypothesis, we're going to assume for a given, let's say an arbitrary, assume for an arbitrary k in the natural numbers that we know that 1 over 1 times 2 plus 1 over 2 times 3 plus and so forth plus 1 over k plus 1 is equal to k over k plus 1. Oops. So we make that assumption, right? So this is the thing which we're going to get to assume is true. And then what we wish to show, that same statement except with k plus 1 in place of k. So this sum needs to go all the way up to 1 over k plus 1, k plus 2. And on the right-hand side of the equation, we should get k plus 1 divided by k plus 1 plus 1. In other words, k plus 1 over k plus 2. So here's our inductive hypothesis, and here's the thing which we want to try to prove is true. And astutely, you notice that the only difference between the left-hand side of the thing we're trying to prove and the left-hand side of the thing which we've assumed to be true is this single term at the end, 1 over k plus 1, k plus 2. So how do we communicate to the reader that we're establishing this identity by working from left to right? Well, to do that, we'll just start by taking the left-hand side of this equation. So here is the whole sum that we're trying to make an inference about. But we notice that the first k terms of that sum, so everything up until that final plus sign, according to our inductive hypothesis, is equal to k over k plus 1. So, you know, on my, whoops, that didn't quite come out the way I meant it to. There we go. So this whole part from 1 over 1 times 2 all the way up to 1 over k plus 1, we know that that's equal to k over k plus 1 when we've assumed our inductive hypothesis. Right? So we'll just replace that part with k over k plus 1. And somewhere we will make the connection for the reader that the reason we can make that replacement is because we have taken the inductive hypothesis. So I'll say that somewhere here, by induction hypothesis. Looks like I need an equal sign somewhere. I'll just put that there. So that's equal to k over k plus 1 plus that last remaining term. And now here's where the rational fraction arithmetic that we were doing before comes in. Right? We'll just get that common denominator and make this k times k plus 2 plus 1 divided by k plus 1, k plus 2. I'm forgetting my equal signs in too many places here. There we go. That's equal to that, which is equal to that. And now we do the arithmetic in the numerator. K squared plus k plus 2k plus 1. K plus 1, k plus 2. And again, how many of these algebraic steps that we show really just sort of depends on the audience, right? probably if you see a proof like this in a textbook or in a more upper level textbook, they're going to skip a lot of these algebraic steps and just sort of assume that the reader can fill them in. But by doing that skipping, you're making an assumption about the reader's mathematical confidence in filling in those details. So at an introductory proofs level like our course, I would say leave as many of them in as you can stomach. It also helps make it easier for somebody reading it to catch any errors, and that somebody should include you, right? Better that you catch an error in your logic than somebody who's evaluating your work catches it. So we cancel one of those k plus 1 factors out of the numerator and the denominator, and we're left with k plus 1, k plus 2 as desired. So then this is what it ends up looking like, right? We have this whole big thing on the left-hand side, and then we take the first k of those terms, and we replace them using the induction hypothesis by k over k plus 1. Then we just do the arithmetic on that expression, sufficient to show that it's equal to k plus 1, k plus 2, k plus 1 over k plus 2 as desired. Thus, by the principle of mathematical induction, we have proven this statement for all natural numbers n. Oops, put a little square in there for the end of the proof. There we go.